Okay, this mini lecture is on some more mathematical ideas regarding rotational momentum. So how do we think about momentum in the rotational sense? How is it related to our translational momentum or linear momentum? And then how do we change it? How do we get it? How do we do problems with it? So rotational momentum is the inertia of an object rotating, similarly to the way that linear momentum was sort of that inertia of a moving object. So the object of a rotating object, the object's resistance to change its rotation. If we go back to our linear momentum, we might recall that the linear momentum was related to both the mass and the velocity. So the faster something was going, the harder it was going to get to change its motion. The more massive something was, the harder it was going to get to change its motion. Well, similarly, we have the same type of relationship for rotational momentum. We use the letter L to define rotational momentum. Okay? And we know that if something is rotating really fast, it's going to be hard to change its motion. Imagine a wheel that's spinning really, really fast. It's hard to change its motion. It's hard to change its rotation. And so we know if we increase omega, rotational speed, rotational velocity, we're going to increase the resistance to change that motion. Well, that's similar to the linear momentum. And if we think about the other piece, the mass piece, we want to keep in mind that for momentum, we want to kind of think of that rotational mass. The idea that mass depends on also what axis the object is rotating about and how that mass is distributed about that axis. And we call that the moment of inertia I. So if I increase I, if I increase the difficulty to get something to rotate, the inertia of rotation, I'm also going to increase the rotational momentum. And we find a very strong parallel to our linear momentum, that rotational momentum is equal to I omega. All right. Well, we know that linear momentum is a vector. Rotational momentum is also a vector. But the direction is a little funky, okay? So the way we find the direction of the rotational momentum is that, and again, this is going to be backwards in the video. So take your right hand. So take your right hand. And if you have a spinning, imagine that you have a bicycle wheel. So here's my bicycle wheel, and there's the axle. And so it's spinning in the horizontal plane. So I'm holding the bicycle wheel, and it's spinning this way. If I curl my fingers in the direction of the spinning, so using your right hand, if you curl your fingers in the direction of spinning, the direction of the momentum is given by your thumb. Okay? So if I have an object spinning like this, if I curl my fingers in the direction of the momentum, in the motion, the rotation, my thumb gives me the direction of the momentum. So there is direction associated with linear momentum. Angular momentum, rotational momentum. And it happens to also be the same as the direction of the angular speed. All right. Well, that's just a general sense of what rotational momentum is dependent on. But how do we change rotational momentum? How do we give an impulse like we do with linear momentum? Remember, to change an object's momentum linearly, we had to apply a force through time, so during time. Well, we know to change an object's rotation, we have to apply a torque. And so if I apply the force to change momentum, perhaps applying a torque will change an object's rotation. You can imagine if something is rotating and you wanted to get it rotating faster, if I were spinning that bicycle wheel and I wanted to get it rotating faster and faster and faster, well, I'm going to apply a torque to get it to rotate faster and faster. Remember, not only that, but a torque causes a change in rotation. Change in rotation, a change in momentum. So Newton's second law for rotation is the same as the idea of impulse in rotation. the same way that it was for the linear motion. So we know that a change in momentum is going to be the net torque times time. So in order for me to change an object's momentum, I'm going to apply a net torque through a certain amount of time. All right, so a bigger change requires a bigger torque, or that torque being applied for a longer time. So this is the idea of impulse when it comes to linear momentum, rotational momentum. Then the final concept we need to deal with is the idea of conservation of momentum. Well, conservation of momentum relates to rotational momentum as well. Okay, so just like linear momentum was the final momentum is equal to the initial momentum, the final momentum rotationally is also equal to the initial momentum of the system. So let's take a really easy system, like the system of a single person. And imagine a figure skater. And that figure skater is rotating, spinning. And her arms are out and she's very poised. Well, she has a certain moment of inertia based on the fact that her mass is distributed away from her axis. It takes a certain amount of rotational inertia to get her to rotate. And she's rotating at some angular speed. Well, we all know that figure skaters can spin really fast. But they don't start out that way, right? They initiate the rotation, applying a torque to their feet and the skate blade. They initiate that rotation with their arms out. And as they bring their arms in, what happens? Well, as they bring their arms in, they are decreasing their rotational inertia. So they're going from a rotational inertia and they're bringing it down. They're bringing their arms closer to the axis of rotation, redistributing their mass to be closer to the axis, thereby decreasing the rotational momentum, the moment of inertia. Well, if this has to be equal, then the only way that can happen is if there's an increase in the angular speed. And what do we see when ice skaters bring their arms in close? They start to spin really fast. And so we're only going to use conservation of rotational momentum in a generic way, in a conceptual way. Thinking about if I change the moment of inertia for an object that's spinning, then I have to change the spinning so that the conservation of momentum stays the same. All right, so 3 ideas to think about in terms of rotational momentum. Just the idea of what it is, the fact that it's dependent on the mass distribution, the rotational mass, we might call it, as well as how fast the object is rotating. To change momentum, well, to change an object's rotation, we apply a torque. So to change an object's momentum, we have to apply a torque, and we do that over time, similar to the way we change an object's linear momentum. And just like linear momentum, angular momentum is also conserved, such that if I have an object spinning and I change its rotational moment of inertia, I will change its angular speed accordingly. All right, good job.